Hello, welcome back to Algebra. Here we're going to talk about an overview of systems of linear equations. And what I mean by that is I want to take this lesson to explain to you what a system of equations is in algebra, general ideas about what a solution to a system of equations really is, and some different cases that we're going to have to be on the lookout for. In the next several lessons, though, we're going to have different ways of solving these systems of equations, and we're going to break it down into different kind of topic areas, right? But this is an overview lesson. We're trying to talk about what is a system of equations, what is a solution to a system of equations, and most importantly, I want you to come away from this understanding why we care, right? I don't want to go on and on about it now. I'll summarize at the end. But I am going to tell you that I teach a lot of other classes, right? Not just straight math classes. I teach a lot of circuit classes, electric circuits, right? And also a lot of physics classes and chemistry classes and all these other classes, mechanics classes, right? I'm not exaggerating when I tell you that what you're going to learn here in the next few lessons about systems of equations and how to solve them is probably one of the most useful things that we do in engineering and in math and science. Because, you know, right now it's just going to be equations with x and y, and you're just going to learn how to solve them, but they're not going to mean anything. But when you take a class on electric circuits, or in a class in rocket theory, or a projectile motion for rockets going through space or something, then almost every problem is going to end up becoming a system of equations. For instance, if it has current, if it's about electric circuits, you might, instead of x and y, we'll probably have our equations in terms of current, electric current, and voltage. And I'll have a whole system of equations that we'll have to solve. And we're going to get the answers to that, and we'll get the current and the voltage as the answers. So if anybody ever asks you, why do you learn this stuff? Why is it important? Who cares about solving systems of equations, even though you don't know yet about maybe current and voltage in circuits or other things that I could talk about lots of examples. It doesn't have to be that. Then in the back of your mind, though, I want you to know that these things are used. Everything that you use that's electronic has been designed by somebody who solved a system of equations. I promise you, it is that important. So let's jump right in. The good news is actually, sorry, I forgot to tell you the good news. The good news is it is not hard at all to do this stuff. So we're going to take it step by step so that you understand why it's not hard. So before we get to the concept of a system of equations, I want you to consider this line. Right? You all know what lines are, right? So we're going to draw one, or I'm going to write one on the board. This line, x minus 2y is equal to 5. It's a line, you know it is because it's in standard form, ax plus by equals c, right? Now, I'm not going to solve it, but I'm going to tell you that it has a solution. It has a solution, 3, negative 1. You remember, when we have all of these lines, they always have solutions because there's two variables. You have to, when you give a solution, you have to give an x and a y, and so they're always a pair of numbers, right? How do we know that that's a solution? I haven't solved it, but I'm just telling you that this is one of the solutions. How do you know? Because if you plug these values in, for x it's 3, so we'll call it 3 minus 2 times y, which is negative 1, is equal to 5, and it has to check out. So you get 3 plus, because, well, let's do it the right way. Let's make it 3 minus. Here, 2 times negative 1 is negative 2 equals 5, which is 3 plus 2 equals 5, which is check because 5 equals 5. So there's lots of solutions. There's an infinite number of pairs of numbers that work here. And you already know that every solution to a line, it's just the points that are on the line. That's what the solution to the line is. It's the pairs of numbers that when you plug them in like this, they all work for that particular line, right? So because lines have an infinite number of points, there's an infinite number of these pairs, these solutions we call them. So just keep this in the back of your mind. We can take a solution, we can substitute it in, and it works. So we know that it's a solution, right? Now I want you to consider another line. Consider this line. This line is not the same as the first line, I will tell you that much. It is this. It's 4x plus 3y equals 9. This is a totally different line. It's not the same line as the original one here. But I'm just going to tell you, without proof, that 3, negative 1, the same point, is also a solution of this line. How do we verify it? Well, let's plug it in here. So it'll be 4 times the value of x, which is 3, plus 3 times the value of y, which is negative 1, does it equal 9? Here we have 12. Here we have negative 3. Does it equal 9? Yes, 12 minus 3 is 9. So all I've done so far is I've said, hey, here's a line. We're going to graph it in a minute, but right now just say there's a line. It has a solution. How do we know it's a solution? We plug it in and it works. Here's a totally separate line, not the same line, totally, completely different angle, slope, and everything. And it also has this exact same point as a solution. How do you know? You plug it in there and it works. Okay? So what this means is that this point right here is on this line. If we were to graph this line, then this point would lie on the line somewhere. And it also means that if we were to graph this line on a graph paper, then the same point would also be on that line, right? Because if a point is here, you know, all kinds of lines can go through the point. So this line has to go through this point, and also this line has to also go through this point. So what it means is that the point 3, negative 1 is an intersection point of both of those lines. Because in your head, like even me, in my head, I don't really know what this line looks like. I have to graph it just like you do. And I don't know what this line looks like. I have to graph it just like you do. But what I do know is that since this point lies on this line, and the same exact point also lies on the other line, then the only way that can be true is if the lines cross some sort of way. And right in the middle where they cross is 3, negative 1, because it has to be on both lines. So we say that that's an intersection point, right? So what I want to do is I want to graph both of those lines. Even though I've kind of demonstrated with my hands, that's not really great. I want to show you exactly what I'm talking about. So the first line was x minus 2y equals 5, and the second line was 4x plus 3y is equal to 9. So how would we graph them? We do it the same way we always graph lines. We solve for y, because we're going to put it in the easiest way we can. Negative 2y equals negative x plus 5. We just subtract the x from both sides, moving it to the other side. And now we have to say that y is going to be equal to negative x plus 5. That's on the right-hand side, but we'll divide by the negative 2 there to get y by itself. But when we do that, we already know, we've talked about it many times, that when you have something on the top divided by a single thing, it's the same as negative x over negative 2 plus 5 over negative 2. Because, and I've said it about 20 times in different places, this is a common denominator, so if you were to add them, you would have that as your denominator and you would just add the top. So you can combine fractions to get this, or you can break them apart to get this, right? So what you have is y is equal to 1/2, positive 1/2 x minus 5/2. Because you have 1 on top, 2 on the bottom, so 1/2, the negatives cancel. The negative here floats out in front, and then you have 5/2. So here essentially is just exactly the same equation as this one, but it's just easier to graph. Now before we graph them, I'm going to go to the other side, and we're going to solve for y here. So we're going to have 3y equals negative 4x plus 9. All I did was subtract 4x from this side, so I have to subtract it from the other side. And then I solve for y by saying negative 4x plus 9 over 3. But it's the same exact thing. I can break it apart. So I have negative 4/3 x, make sure you understand that, plus 9/3. All I did was say the negative 4x is divided by the 3, and then the 9 is divided by the 3. So what you have is negative 4/3 x plus 3. Negative 4/3 x plus 3. Just double checking my work here. It all looks to be correct. All right, so how would I graph this line? I know this, the y-intercept is negative 5/2, and the slope is 1/2. So let me go over here. What is negative 5/2? That's negative 2.5. So the y-intercept of the first line, here's negative 1, here's negative 2, here's negative 2.5. And the slope is rise over run, 1 over 2. So I'm going to go up 1 over 2. So if I'm doing my math right, the secondary line should be something like this, right? Something like that. All right, so then what I'm going to do, just double checking myself to make sure I don't screw something up that's, you know, no good reason for. So this is, you know, as best I can do here. It's not going to be exactly perfect, but this is going to basically be that first line. All right, so here we have a little double arrowhead here. And this guy is, you know, I should have drawn it in blue, I guess. Sorry about that. But anyway, it's 1/2 x. Let's just double check where is it going to intersect. Yeah. So this is 1/2 x minus 5 halves. That's what that line is. Now how do we graph that second one? This is the second one. The y-intercept is 3, but it has a negative slope. So let's go put the y-intercept. Here's 1, 2, 3. This is the y-intercept of the first one, but then I have to go down 4, not up, down 4 over 3. So 1, 2, 3, 4 over 1, 2, 3. Here's the other point on that line. And I'm going to do my best to draw this as an intersection point. Something like that. All right. And then this guy, I'll just write the equation. Y equals negative 4/3 x plus 3. Now, I gestured with my hands earlier, but what we basically have proven is that this point, 3, negative 1, lies on this first line. Now, let's just double check. The purple line, right? 3, negative 1. Here's 3, negative 1. It does lie on the purple line. The second line is this one. 3, negative 1 should lie on that second line. The second line is the blue one, so it all 3, negative 1, 3, comma, negative 1 also lies on it. But notice the intersection point is plain as day right here. It's 3, comma, negative 1. So you see, what we're trying to say is that a point can only lie on 2 totally separate lines at the same time if those lines cross each other. We say that they intersect each other, right? And if they intersect each other, they lie on both of those lines. Now, I didn't want to scare you with the terminology, but when we have 2 lines that cross, then we say that those 2 lines form a system of equations, because you have obviously equation number 1 and you have equation number 2. You can find solutions to number 1, lots of them, infinite number of solutions, because remember, this line is an infinity number of solutions of points that satisfy that equation, this one. And this line has an infinity number of solutions that all comprise all the points on this line as governed by this equation. But only at one point, an infinitesimally small point right here is where they cross, and that is a solution to both lines. So we say that line A has infinite number of solutions, and line B has infinite number of solutions, but when you put them together, there's only one point they cross at. That is the solution to, not to the equation individually, to the system of equations. So I need to write a couple things down. What we have learned here is that, in this case, x minus 2y equals 5, and the other equation, 4x plus 3y equals 9. This thing as a unit, as a combination of things together, this is called a system of linear equations. Why do we say linear? Well, because they're lines. I mean, linear means line, right? So when something's linear, it goes in a straight line. So you know that this is linear because it's in standard form. In all of these standard form things, they form straight lines. So you know by looking at them that they're lines. And so there's only going to be one crossing point. But later on in algebra, we're going to have things that are not lines. They'll look at like a parabola, which is like a big smiley face. It goes down and it goes up again. That's not a line, right? So that's different. So here, but for now, we're talking about 2 lines that cross. They're called a system of linear equations. And the solution to the system, when you solve the system, the solution is only one point. That is where the lines cross. Where the lines cross. So what we're going to do once we get through this introductory lesson, I still have some more stuff I want to show you, but once we get through this introductory lesson, we're going to learn how to solve these systems of equations. There's actually lots of different ways to do it. There's 3 different ways we're going to learn how to solve systems of equations. But the only thing I want you to get out of this lesson is that when you find the solution to a system of equations, you only want one point, and there's only one point that works because it's the only point where both of these lines cross. You're trying to find that intersection point. So the very first method that we're going to learn how to solve systems of equation is just going to be to graph them. We're just going to graph them, and guess what? We're going to look and see where they cross. And if we can pinpoint where they cross just by looking at a graph, we will say that's the solution to that system of equations. Okay? Also, if a solution, or if a systems of equation has a solution like this, if it has at least one solution, we say it is a consistent system if it has at least one solution. And I guess I got to kind of give a little bit of way about the next thing we're going to talk about in order to kind of make you understand it. You're probably like, well, why would it not be consistent? Because anytime lines cross, they're going to have some point where they cross. So they're almost always going to be consistent. Any two random lines that you just draw on paper, they're almost always going to cross somewhere, and that's going to be the solution point. And so we say they are consistent. You can think of consistent, when somebody is a consistent person, they're just always kind of good. They're always doing the same thing. That's what consistent means, right? But when equations, linear equations are consistent, it means that they're well behaved, that they have a solution because they cross. But I want you to think for a second, when would a system of equations not be consistent? Can you think of a case when a system of equations would not be consistent? What I'm asking you is, if it's not consistent, then I'm asking you, can you think of a system of equations where they don't have a solution? Well, we already said a solution is just where they cross. So the question is, can you think of a system of equations where they don't cross? Ever. Like ever, ever. They never cross. Can you think of that? Well, we just talked about that in the last section. If two lines are actually parallel, then they'll never cross. And then you'll never have a solution to that set of equations. So most of the time, solutions of equations are consistent. They cross at a point. But if parallel lines are what we're dealing with, then you won't have any solution. So we're going to erase the board, and we'll talk about that right now. All right, so I gave you a big hint at the very end of the last section. Let's take a look at this system of equations. A system of equations just means you write down two different equations and two different variables unknown, and you link them together and say, I want to find the solution of both of them at the same time. What's the intersection point? So we could have this equation and x plus 2y equals 1. Now, nobody can look at these equations and say, oh yeah, I know what they're going to look like. Well, I shouldn't say nobody, but a lot of people, most people, I cannot look at this and say, I know what they're going to look like. So if I'm going to try to figure it out, I need to solve for y and figure out and graph them. So I'm going to graph this guy by moving x over. 2y is equal to negative x here, and then I have plus 8. And so in order to get y by itself, I'm going to say y equals, now I'm dividing the whole side by 2, but I'm tired of kind of showing you that breaking up thing. What you really have is the first term, negative x over 2, and you have that second term also divided by 2. So I'm just going to start writing it like that. So y is going to be equal to negative 1/2 x plus 8 over 2 is 4. Let me just double check my notes here. Negative 1/2 x plus 4, correct. All right, so then we go over to the second equation here. I'm going to solve for y again. So it'll be 2y equals negative x plus 1. So here I'm going to divide by 2, and it'll be negative x over 2 plus 1 over 2. So just to rewrite it, it'll be negative 1/2 x plus 1/2. So I want to graph both of them, but I know that all of you guys looking at this can see the problem. Because yes, they have different y-intercepts, but this slope of this line is negative 1/2. And the slope of this line is negative 1/2. Now, what did we talk about in the last lesson for the slopes of the lines? Whenever they have exactly the same slope, what are they? They are parallel. That means they will never cross. That means they'll never have a solution. So let's graph the first line. The y-intercept is 4, so that means we're right there. And the slope of that is, like we said, negative 1/2 for both of them. That means down 1 over 2. So down 1 over 2. So those are the lines for the first set here, for the first line. All right, and so there we go. There's line number 1. And I'll try to remember to do the other line in blue. So same thing, 1/2 is the y-intercept, but exactly the same slope. So we have the same y-intercept, different y-intercept, 1/2, but the same slope. So it's down 1 over 2. So that means it's going to be right here. So then when I put a line through here, I will do my best to line it up, make it as perfect as I can. It'll be something like this. All right, this is not perfect. I mean, even though I'm trying to be as perfect as I can. But you can see, though, that these lines are never going to cross. So, yeah, of course, this blue line has points all over the place that exist on that line. That's what a line is. And the purple line has points that are consisting of all the points for that line, of course. But there is no solution to this system of equations as a unit because they never cross. In other words, there is no point that is common to both of them. There is no point that I could plug in and verify that it worked for this line and then also plug the same point into the other line and verify that it works for that one. So because this solution, this system of equation has no solution, you might say something like no solution, or you might say no intersection, right? Right? And more often than not, you'll probably just say no solution. And then what I really want you to know is that when something doesn't have a solution like this, we call it an inconsistent system. So far we've learned about consistent systems. Those are systems where the lines cross, and inconsistent systems where the lines never cross and there's no solution at all. So let me just take my finger and erase both of these little lines because I have one more I want to show you. The last one's actually really fast, but it's the third class of systems of equations that you really need to learn. But it's actually the easiest and the fastest, so we saved it for the end. So let's take a look at a third system of equations. Let's take a look at the first equation, which is negative 3x plus 5y is negative 6. And also negative 6x minus 10y is 12. So here we have two completely different looking set of equations. Now we want to figure out how do we solve them. I mean, later we're going to learn we'll probably graph them to solve them. So let's just go ahead and try to figure out what they look like by solving, solving for y in both cases. So we're going to solve for y. So we'll have 5y. We'll move the 3x over, making it 3x minus 6. And then we'll divide by the 5. So what we'll have is 3x over 5 minus 6 over 5. Just divide both by 5. And so just to clean it up, it'll be 3/5 x minus 6 over 5. So that's the first one. Well, I'm human too, and I made a mistake. Actually, I didn't make a mistake in any of the math here. But actually, and when I wrote the problem down, this should be 6x minus 10y is 12. I'm sorry about that. It's just a small change to the problem. Same thing. We have two equations. We've solved this guy. Now let's go and solve this guy. So what we're going to have is the negative 10y is equal to, move the 6x over by subtracting. So we have negative 6x plus 12. And then we're going to divide by the 10. So we'll have, or negative 10 I should say. So it'll be negative 6x over negative 10 plus 12 over negative 10. So now you have to think about fractions a little bit. I mean, the negative signs are going to go away, but we have 6/10. How do we resolve that? We'll divide by 2, right? So it'll be 3/5. So it'll be 3/5 x. This negative sign will float out, and then let's go and divide by 2 again. So we'll have 6/5. All right? So we get this equation, we get it down to 3/5 x minus 6/5. But the original equation was 3/5 x minus 6/5. Now that's really strange, because I'm telling you it's a system of equations, but when we actually try to graph them, so we put them in slope-intercept form, we actually find out that they're exactly the same thing. So what it means is, intuitively, if you want to really graph this, I mean, you can do it however you want. I mean, this 6/5 is just a little bit bigger than 1, so it's a little bit bigger than negative 1. So it's something like this. That's the y-intercept, and it's 3/5, so up 3 and over 5. So I could go something like 1, 2, 3, and then 1, 2, 3, 4, 5, something like that. 1, 2, 3, 1, 2, 3, 4, 5, right. And then I could go and graph these guys, or graph that line. But still, you're left with the question, what does that mean? Why do I have both of them that look like exactly the same line? What you get when you have something like this, when you have two equations that are a system of equations but actually end up being the same equation, what really means is if you graph this line, you get this line that we've drawn. If you graph the other line, you get exactly the same line on top of it, so I can't draw it again in blue because it'll just wipe it out. But when you think about it, most of the time you're looking for intersection points, right? This is the solution where they cross. But in this case, you found line number 1 that looked a certain way, but line number 2 is exactly on top of it. So it shares every point with that line. It's like it has infinite intersection points. Every single point on line number 1 is also on line number 2 because they're the same thing. So in this case, it's just a really weird out there case, but you have infinite solutions when they lie on top of each other. And this kind of system of equation is called a dependent system. Right? You can't really specify a solution because any point that I pick on this line also fits for this line, so I can't really totally specify a unique point, a single point, but it's called a dependent system. When you get dependent systems in real life, it generally means that it's not good usually. Usually when you're trying to solve a system of equations, you're trying to find one point and satisfy each of those points, or each of those equations with that one point. So what I really wanted to drill down is to show you an example of the 3 kinds of systems of equations that you can possibly get. If you get 2 lines that cross at a point and you find that single point as a solution, it's called a consistent system. It has a solution, has a point, that's the point that works for both lines, it's called consistent. But if you, less rare than that, I should say, or less common than that, or more rare, less common, is if you had 2 lines that never cross. They're parallel, and you can see that from the slopes when you put them in slope-intercept form. If they never cross, we call them inconsistent systems because there is no solution, 0 solutions. There's no points that are common to both lines. But if you get down to the point where you find the slope-intercept form and you actually find the same equation for both, then we call it a dependent system. It really means there's infinite solutions because the lines are the same thing. Why do we call it dependent, by the way? It's because if you look closely at this equation here, you can multiply this equation by something to actually get this equation. It's just a multiple. It's kind of like, you know, you might have A, and then you might multiply, like you might have A is just a variable, right? And then 3A gives you 3 times A. So this thing here, this thing we call 3A, it's dependent on A because it's just 3 times A. So of course it depends on what A is, right? So this equation is this. Just like we can multiply A times 3 and get something else, I can multiply this equation by something to get this one. Can you figure out what it is? Well, if I multiply this equation, this whole thing by -2, -2 times this is going to give you positive 6x. -2 times this is going to give you -10y. -2 times this is going to give you positive 12. So even though those 2 equations initially looked to be totally different from one another, one of them was actually not really independent. It was just a slightly modified form of the other equation. It was dependent on it. So it's not a unique equation at all. It's very similar. In fact, it is the same equation. If I divide this by that term, I can get this back. So what we've shown by solving for y is that they're the same exact thing. But we call them dependent equations because this one's a multiple of that one. So it doesn't lead to the regular normal kind of solution that you want to see. Finally, I'll say that there are several different ways to solve systems of equations. We're going to get into all of them. The first one, in the next lesson, we're going to talk about graphing system of equations. That's just we're going to look at the intersection point and figure out where they cross. The next way is we're going to talk about substitution, where we substitute one equation into the other. And then the third way we're going to learn is how to add the equations together. But all of those methods, they're all trying to achieve the same result. We're just trying to get down to the end where we can find that single intersection point where they cross. That's the solution. And if along the way we find out that they're actually parallel lines, then we'll say that they're inconsistent, there's no solution. And if along the way we figure out that they're actually the same equation all along and it was just kind of hidden from us, then we'll say that they're dependent system and there's infinite solutions because they ended up being the same equation anyway. So follow me on to the next lesson. We'll start our journey of solving systems of equations by graphing.